Okay, this is just simple pre-calculus. Early part of the course where we're doing quadratic functions, but it's good to know and good to understand things in a little bit of depth. So it's kind of a reminder uh, of some of the properties of quadratic functions, which could be relevant to solutions of some differential equations. Things you should know, be aware of, but maybe not totally. So, something you would figure out, but if I give you a reminder, it'll be quicker. So just an example, we sketched a graph of y equals x squared plus 4x plus 4. Quadratic formula tells us that we have only one zero. Okay, -2 plus or minus 0 just gives us -2. So the only zero of the function is here. Now, this is going to be the graph of the function, but how do we get that? Is exactly 1, 0. The leading coefficient, the coefficient of x squared is 1, so that this graph is just a transformation of the basic x squared graph. So here's your basic x squared graph. And we can see then that the vertex of the x squared graph is here. The only way the graph of a quadratic function, which has to be a parabola, and we should understand conic sections well enough to be able to prove that. But that's kind of a stretch given the way the curriculum glosses over the rigorous part of mathematics from the early courses on. The only way a parabola can go through the x-axis or touch the x-axis at exactly one point is if it does so at the vertex. So the vertex transforms, the vertex of the x squared transforms to the vertex of this parabola for reasons that I won't detail. The leading coefficient tells you that we haven't vertically stretched this parabola. And then we can actually conclude then that since this is a translation of the original parabola, -2 units in the x direction, the equation of the parabola has to be the quantity x plus 2 squared. That's how you replace x by x plus 2. You move everything in the everything 2 units in the negative direction. You translate everything -2 units horizontally. We can also see this because you can complete the square on this and you can get the standard form, a times x minus h quantity squared plus k. You don't need to complete the square to do it if you use the quadratic formula because the translation again is -2 units, and x minus h translates things h units in the horizontal direction. X minus h would be x minus -2 because -2 is the translation, which is x plus 2. So we got x plus 2 quantity squared plus k. Well, k would just move things up or down unless k happens to be 0, in which case it doesn't move anything in the vertical direction. Since this point is not moved in the vertical direction, k has to be 0. So this is the y equals x squared graph shifted 2 units to the left and raised k units, but k has to be 0 in this case. To do this parabola, we can calculate the zeros by the quadratic formula. We get something like -4.95, 0.95, meaning we have now a picture where the zeros are here and here, and the axis symmetry has to be halfway between the two zeros. Well, the zeros are at -2 plus or minus the square root of 24 over 2. Square root of 24 over 2 is about 2.95, which means that -2 is right in the middle. So the -4 over 2 gives you the axis of symmetry. So all that is worth keeping in mind. Okay, well, so much for that. I'm going to pause the video for a second and just this is a solution to the equation x y prime minus y equals x squared sine of x. And you said that this solution was valid over all possible real numbers greater than 0. Not quite right. Okay, now if this is the only restriction, the 1 over x times y, then you would have been right. Okay, but you have a restriction over here. Wait a minute now. When I looked at the cosine and the sine, I thought you were going to get a tangent, but you don't. So for some reason, oh, no. Never mind, that's not what you said. You said the interval was is the interval 0 to pi over 2 is your answer. It's not quite right. Now there's got to be some initial condition that limits you to the it says the largest interval. Okay, as I said before, the only restriction is you have reciprocal of x. Now, if you had a tangent over here, then this would have been a good solution, but there's no initial condition given on this solution. So it seems like the only restriction is that x can't be 0 because of the 1 over x here. Everything else is defined for all values of x.
Well,
so,
that's what I thought. That I'm pretty sure was one of my answers. I put from negative infinity to 0, open integral union 0 to positive infinity. And I think it still counted that as wrong.
Yeah, it would, because that is not a single interval. That's a union of two intervals. So if you have a solution in one of those intervals, if your initial condition dictates that you have a solution in for a positive value of x, then it would be 0 to infinity, but it could indicate there's a solution for a negative value of x. There's nothing in here that prevents x from being negative. So that's your only restriction with the largest interval. Could be negative infinity 0 or 0 infinity. It's a little bit confusing that they said the largest interval. Either that or I'm missing something, and that's possible because my brain doesn't seem to be totally connected this morning. But I think I got most of that out of the way earlier. And I don't see a reason why X has to be positive. Okay, now if I draw out the direction field and look at phase pictures and so forth, I might see a reason, but I'm just looking at the equation. I don't see one. So I'll leave it to you to think about why the book might have said, or the web assign might have said only this interval without mentioning this one. Be interesting to see whether they count it right if we use the negative infinity 0. So without going any more deeply into it, that's it. And you're right that there are no transient terms. Transient term basically means a term that goes to 0 as X goes to infinity or negative infinity. So if X is regarded as time, then you would just be looking at time going to infinity. But both of these terms remain finite. As X goes to infinity. They don't approach 0 as X goes to infinity. Okay, well, again, I'm going to kind of leave it as a mystery why the book didn't include negative infinity 0. Maybe take a look at that later. Okay, a general solution to the differential equation here, and the equation is 1 plus xy prime minus xy equals x plus x squared. Well, that's going to give you y prime minus x over 1 plus x y equals x. Okay, when you divide by this. And of course, you're going to restrict your domain, and you did that correctly. So the domain would be -1 to infinity. And that's the largest interval. Again, I don't see why x couldn't be negative. So negative infinity, -1 is just as big as 1 infinity, because you can do a one-to-one correspondence between both of those sets. But I'm not going to mess with that. So that this is a linear. Integrating factor is e to the capital P of x. Now, this is a little different than your book's notation because they use a capital P. I use a small p for this function, and that's what I did last time. But anyhow, this would be e to the integral of x over 1 plus x dx. Okay, well, integrate x over 1 plus x dx, that u equal 1 plus x, du is going to equal dx, and x, of course, is going to then be 1 minus u. So this becomes the integral of 1 minus u over u du, and that's the integral of 1 over u du minus the integral of -1 du, which gives you the natural log of the absolute value of u plus u. And we don't worry about integration constant because we're going to end up exponentiating something, exponentiating that integration constant, which just gives us another constant. Okay, so anyhow, you have this. So, and of course, expressing this now in terms of x, you have the natural log of the absolute value 1 plus x plus 1 plus x. Now you multiply both sides by the integration constant. Can you see the bottom of the board there? Because I'm still looking at the problem. Yeah, we've got that. Okay. So if I've done this integration correctly, I just multiply both sides by this mess, the sides of this equation, and this side will end up being the differential of this function. Okay, so we get natural log this times y prime minus, well, we'll do it in the same, natural log of the absolute value of 1 plus x plus the quantity 1 plus x times x over 1 plus x y equals natural log of the absolute value of 1 plus x plus 1 plus x quantity times x then is a little more complicated. This left-hand side should be differential. We'll write this as dy dx. Well, let's write it out. Natural log of the absolute value of 1 plus x plus the quantity 1 plus x dy minus the quantity natural log of the absolute value of 1 plus x plus the quantity 1 plus x times x over 1 plus x y dx equals natural log absolute value 1 plus x plus the quantity 1 plus x times x. Doing it in my head, not quite seeing it, how it's going to work out, but it should work out. This left-hand side should be the differential of natural log absolute value of 1 plus x plus 1 plus x times y of course, that should be the differential of natural log absolute value of 1 plus x plus the quantity 1 plus x times x. When we integrate this differential, that should give us natural log of absolute value of 1 plus x plus the quantity 1 plus x y. And then that should be the integral of this differential. Probably I'll need to use another set of parentheses to clarify that. integral of x natural log of 1 plus x plus x times 1 plus x dx. And then you do this integral, and then you solve for y just by dividing this integral by this coefficient. Okay, well, I don't want to work out the rest of it. That's the process. X times the natural log of 1 plus x is easily enough integrated. You let u equal 1 plus x again, and you get u minus 1, similar to what you got here. And I mean 1 minus u, same transformation over here. So this is straightforward to integrate. And this is really straightforward to integrate. It's just x squared plus x. And the rest of it should come out. Then you have some rearrangement to do because you're going to have a natural log out of this integral. You're going to have to solve for the natural log in a way very similar to what we did with the logistic equation last time. So it's a little bit complicated, but it works out. And I think this is in the section on linear equations, yeah, because everything looks like a linear equation. Okay, then number 4. I think number 4 is going to involve similar integrals. Did I just do number 4? Yeah. Okay, so that was number 4. It's number 9. Number 9 is going to involve a whole lot of the same stuff. I think the integral is going to be a little simpler, but the process is going to be the same. So the form of your solution your solution looks okay. It's just that it looks like WebAssign just didn't accept your solution. Your solution is, well, natural log of x plus c in the numerator with an x plus 1 in the denominator. Your book wanted that separated. It's like you got a plus b quantity over c. They wanted a over c plus b over c, and they didn't accept quantity a plus b over c. So I'm going to give you a couple of points back on this. That's a little bit harder to do with WebAssign, so I don't want to navigate that right now. So you might want to email me. And then the largest interval over which the function is defined, you're saying -1 infinity, which on the surface of it, I would agree with, except the natural log of, natural log of -1 isn't defined. Okay, so you got a natural log of x in your solution, a natural log of -1 isn't defined. As far as the equation itself, the -1 infinity is the region in which the equation is defined. But you still have to look at your solution and see if your solution's defined. So that little detail got by you. So you want to be careful about that. Look at the domain of the function you get when you do the integral. Otherwise, it's a pretty good solution. Anyhow, I'm going to give you a half point back, but don't rely on me to remember to do that. Email me. Just say, hey, give me that half point on 2.3 or 2.4, 2.3. Okay.
Okay.
Fair enough.
Thank you. Yes.
Okay. So again, I don't see anything else to mention on your solutions. And come on. Okay. I think the next section is exact equations. And exact equations are pretty straightforward until you get to the whole idea of integrating factors. So let's go over some of the details. And let me also look ahead. That's going to be due on Tuesday. And maybe give you a little bit of head start on Thursday, which is just homogeneous and Bernoulli equations. It's kind of neat stuff. I think there's a Bernoulli equation, and I'm looking at the homework and I don't see one yet. There we go. That one's Bernoulli. And that one's going to be Bernoulli. Okay. So you got a couple of homogeneous equations, a couple of Bernoulli equations. And Bernoulli equations are pretty neat. One thing that the book often stresses, and I think I even copied their statement, so I'm going to give you the literal statement if I can navigate. And this comes from section 2.5, actually, but it applies throughout because they mention it. Now we got to format it, word wrap, now navigate, and then. Okay. The book gives the advice at the one point of one of the solutions, either the homogeneous or the Bernoulli solution, and it's not important what the solution is. At this point, we offer the same advice as in preceding sections. You've already seen the advice. Don't memorize anything, especially formulas for solutions. Work through the procedure each time. Don't cut to the formula. Work through the entire procedure as it's defined in the book, because the formula will get you the answer, but it won't give you the insight. And I think you're pretty good at that, but I'm going to just mention it anyway as a reminder, because I really like that statement. Okay, well, let's go ahead and do something here. I don't remember if I've got the back of this board. Yeah, I have it. Okay, we're looking at exact equations. Okay. Example of an exact equation. I'm going to give away the way I make up problems for tests. Okay. We pick a function of two variables. Okay. And when I do that, I'm going to say let f of x, y equal something pretty obvious, x squared y cubed. I'm going to say then plus cosine of x. Find the differential. Well, differential of a function of two variables is just the x derivative times dx plus a y derivative of dy, and hopefully you remember what all that means and how it works from multivariable calculus last semester. If you don't, quite simple. If you don't remember it off the top of your head, you will once I do it. So fx is just 2xy cubed minus sine of x dx plus 3x squared y squared dy. Okay, then we set df equals 0 to get a first order dE differential equation. And then confuse the issue by rearranging the thing. And if you rearrange this, you can get, I'll put it in this form, dy dx equals, well, how do we get dy dx? Put the dx over on the other side, going to get a negative here. And then divide both sides by this term, this negative term. And you get dy dx on one side, and you get, actually divide by this term, but you get 2xy cubed minus the sine of xy over 3x squared y squared. Okay, now that's really confused. Okay, there's no way most of us can look at this thing and tell that it's of the form df equals 0. So solution to df equals 0 is f equals constant. So the solution is x squared y cubed plus cosine of x equals constant. And you can solve for y. Y equals the cube root of c minus cosine of x over x squared. If I did my algebra correctly, and I made totally stupid arithmetic mistakes in my linear algebra class today and wasted about 15 minutes, and maybe confused some people. So who knows if I even wrote that down right. My head is stuck on this because I think if I subtract cosine x from both sides and then divide by x squared, I get y cubed. And if I take the cube root of both sides, this is what I get. Don't believe me, work it out yourself. Okay. Okay, well, that's great. That's a solution to this differential equation. But if you don't know that this differential equation came from this, what are you going to do? Okay. It's great if we know f of x, y. What if we don't? What if all we're given is this equation? The question is, how do we discover f of x, y? Well, it actually turns out to be pretty easy. But we need a little bit of, okay, well, let's see. Put into the form three x squared, y squared. Actually, I want to write the dx first. That's the way you usually see it. That wouldn't be wrong to write it the way I was about to. But I'm used to writing it in that order too. Since my brain isn't totally functional right now, I'd better write it in the order that I'm familiar with. But it's the order you're going to want to see anyway, so it's good for both of us. Okay. So I want to write the dx. Well, rearrange this. I can get it into the form 2xy cubed minus sine of xy dx minus 3x squared y squared dy equals 0. Okay, now I want to use the right letters, and I think we let M stand for this and N stand for this. Wouldn't make any difference to me, but you're going to be a little more notation dependent. And I actually wrote down to remind myself which way your book does it, and I'm wrong. Okay, so we're going to write this as excuse me, form is N dx plus M dy equals 0. N equals 2xy cubed minus sine of xy. M equals 3x squared y squared. Now I'm going to observe something that follows directly from the fact that this equation is ultimately the equation df equals 0. Okay, if you trace this through, the coefficient of dx is this, coefficient of dy is this, and I've got a sign problem, SIGN problem. I knew to do it, but I didn't. That is consistent with the fact that my brain isn't working great. Setting this equal to 0, if I switch sides, one of these is going to become negative. So I'm going to have to change signs here before I go on. If I don't think it's going to work out. If I discover that I'm wrong, I can go back and change the signs again, because again, I pretty much don't know what I'm doing right now. But here we have it. And of course, now this equation is the same as this equation. Okay, so by rearranging the equation into this form, I get this equation, which is df equals 0 for this function, but we still don't know that that's going to work. Okay, now if that does work, well, this thing is your fx, and this thing is your fy. And so if that is the form, then n equals fx and m equals fy. Well, so what? Well, here's so what. So if n equals fx and m equals fy, then ny equals fxy, and starts with the A, ends with the D. I started to write a D. Okay, then that's nx, that's fxy, ny equals fxy, what I just wrote, and mx equals fyx. Well, your order of partial differentiation makes no difference. And certainly, if you didn't remember that, it just jogged your memory, because you knew that perfectly well a couple of months ago. Okay, so we use this. So if this thing is of the form df equals 0, then you're going to get this. If it's not of the form df equals 0, it ain't so, then you're probably out of luck. Okay, but maybe not, because you might be able to do something with an integrating factor. So I'm going to write it, going to be in the watermark. All I'm writing here is but, maybe not. If you have an integrating factor as a function of one variable, and you can do an integration, then maybe it's okay, but we'll see that in a minute. Yeah, in a few minutes. Okay. I think I can do that on the small board, the big board. I got to cut one of those big boards in half. And I got batteries, I've got the saw, I've got a sawhorse set up. I can do it in 2 minutes if I thought to do it when I have time to do it. Okay, so what does this tell us? Okay, well, let's test. ny is the y derivative of this. And when I wrote down sine of xy, every time I wrote down sine of xy, it was wrong. It would work, but remember f was cosine of x, not the cosine of xy. And I got a sine of x here. But then when I wrote it down here, I did sine of xy. Okay, not so. And I was okay here, but then I wrote down a sine of xy here, and I wrote down a sine of xy here. And it's not the sine of xy, just sine of x. Okay, the sine of xy, this thing wasn't going to work. So I was careless. I think I had an xy in something I did earlier, and still there, echoing around in my empty head. Okay, so ny, now if we've got the right n, is easily found. It's going to be 3y squared times 2x, okay, which is 6xy. Sine of x has 0 y derivative. Mx equals 3x squared y squared derivative with respect to y, so you're going to have a 2y times 3x squared, which is 6xy. Okay, so the equation is a form df equals 0. Well, now we got to find f. Okay, how are we going to find f? So good, now what? Got to find f. Well, if this is the form f df equals 0, we know now, after having made this test, that n equals the x derivative of f. So f is an integral of n with respect to x. Okay, well, also m is fy, so f is integral of m dy. Now let's make sure we understand why n equals fx and m equals fy. How do we get n and m? Okay, we started with the equation, we rearranged it, and we assumed that this form is n dx plus m dy, and the form is df equals 0. Well, df equals 0 means fx dx plus fy dy equals 0. So whatever's in front of the dx has to be fx. Well, this is what's in front of dx. N is in front of dx. M is what's in front of dy. And of course, that's fy dy. So fy is m. So we want to make sure we understand all those connections. And a good way to do that is just make up some not too complicated function, do its differential, then pretend you don't know and do what I'm doing here. Because it's exactly what I'm going to do when I make up a test. I can make these things as ugly as I want, but they're going to be integral. And the integral is not going to be that difficult. So if you know the process, you'll be okay, no matter how ugly the equation is. You just got to remember to do this test, and then everything kind of rolls out in a very straightforward manner. Okay, so understanding all this, we do the integration. Now there's a little trick to the integration. When we're integrating with respect to x, we're going to get an integration constant. And that integration constant could be just a constant number, but as far as x is concerned, any function of y is also constant. So when we do the integration here, the constant is going to be an arbitrary function of y. Might just be a constant, might be 0, might be some fixed number. And similarly, when we do the integration of m with respect to y, any function of x is going to be constant with respect to variation in y. Okay, so we're going to do that. Okay, so let's just do the integrals. The integral of n with respect to x is the integral of 2xy cubed minus sine of x dx. And that integral, well, very simple, integral of 2xy cubed with respect to x, only the, 2xy cubed is constant, that kind of comes out of the integral. And just integrating x dx, you're going to get x squared over 2. So you can easily verify that that's going to give you just x squared y cubed. And notice that there's our f function, and we've already recovered this term. And then, of course, you're not going to know that. You're still in the dark. You don't know what this is a solution. You got to discover that this is a solution and verify it. So now you got x squared y cubed plus cosine of x. Now, actually, you're done, but you don't know it. Okay. This is our integration constant when we're integrating with respect to x. In other words, this antiderivative could be this function because if you take x derivative of this is what you're going to get. The x derivative of g of y is 0. So that's what we write. And usually we're going to need that. Whether we need it now or not, we'll see. Okay, well, m is the 3x squared y squared. Okay, again, right there, we have it, because we have 3x squared y squared dy. That has to be your y derivative of that f function. M dy then is, or the integral of m dy is 3x squared y squared with respect to y. And that's just x squared y cubed. That's obviously a very simple integral. But then we have to have an integration constant. Since f has to equal n dx, the integral of n dx, and f also has to equal the integral of m dy. If that's the integral of m dy, we're never going to get that cosine x. These two won't resolve. So if we remember that our integration constant with respect to y is g of x, now we can resolve them. Okay? In order for this integral to match this integral, and that's f, both of these integrals have to equal f. In order for this integral to equal f, since this integral has a cosine of x, this g of x has to equal cosine of x. So I can say to reconcile, That's not quite right, because we can still have a constant. Okay. So f has to then be x squared y cubed plus cosine of x plus c. This agrees with this solution as long as your g of y is equal to that constant. This matches x cubed, x squared, I hate those smudges, x squared y cubed matches if g of y also equals c. We've got our solution. Okay, f is x squared y cubed plus cosine of x plus c. Now, in this case, c was 0, but of course, nothing would change if we added an arbitrary constant to f of x, y. All right, now, our conclusion is, I hate not to be able to lift this with my right arm. My shoulder's kind of locked into my scapula, it doesn't go that high. Okay, so the solution of the function that I can no longer see, but we started with this so I can recover it. So solution of 2x squared y squared. Actually, let's just go back to the equation as I gave it. And let's see if I can do that in my head from this. Okay, so dy dx would be the y derivative of this in the denominator, the x derivative in the numerator. So it would be 2 I'm doing something about P. Can't trust the old brain this morning. No, it's right. Okay. Except I was going to forget that negative sign. This n over the y derivative, which is 3x squared y squared, is f equals constant. Since the equation is df equals 0. F equals our original function, which was x squared y cubed plus cosine of x. And then I tacked on that plus c. So we worked our way all the way back to where we started, which was here. The solution is x squared y cubed plus cosine of x plus c equals a constant. Well, now we see that the constant here that we tacked on in the integration is unnecessary, because whatever constant we tack on can be absorbed into the constant that you get from the fact that df equals 0, so f is constant. Okay, and of course, get rid of this now. That's exactly what we got here when we knew what f was. So we went through all this to discover f, because of course, when I make out this problem, I'm not going to tell you what f is. You got to go through the process. And that's the same thing your book is going to do. So when you've got an exact, this is called an exact equation. Okay. So it's this, and the process works. The only caveat is you can't always integrate the expressions you get. So maybe you're going to get an implicit solution. But generally, you're going to be able to do the integration most of the time. Okay, now, an equation doesn't really have to be exact to be made into an exact equation. So I'm saying, if it isn't exact, it might work if we try to find an integration factor, an integrating factor. U of x, y. Now you saw this process used in solving a non-homogeneous first order differential equation. Matter of fact, we did it earlier, okay, where we had that one differential equation and we multiplied by the e to the integral p of x dx, both sides. So you should recognize what we mean here if you've gone through the entire process. So I'm just advocating you go through the process. You don't just memorize formulas and stuff. So you get a feel for what an integrating factor is. Now, integrating factors can get totally incomprehensible. There might be one, you'd never find it. And in general, for this course, that's what's going to happen. Turns out if mu is regarded as just a function of x or just a function of y, sometimes you can get away with that. Okay, so what you're looking for is If it works out, then this is going to become exact. Okay, well, how does that happen? Well, if it's so, then the y derivative of the dx would have to equal the x derivative of the dy. For reasons that if you don't totally understand, you probably go back and see why that was, starting with the assumption df equals 0. But there you have it. And of course, mu ny is mu yn plus mu ny, and mu mx is mu xm plus mu mx. Okay, well, that makes it easy, doesn't it? Well, no, not really. Okay, we could rearrange this to where we put the terms with the ny and mx on one side, and those terms will just have mu, and then the terms with mu y and mu x on the other side. Makes a certain amount of sense to at least try that and see how it works if you're exploring this possibility. So if we do that, we get mu times mx minus my on this side, and then mu yn minus mu x m on this side. Well, we know all this. Well, we don't know mu, but we can calculate this. So we know this, it's just a function of x and y. Okay. Over here, though, uyn and uxm, of course, we know n and we know m, but this involves partial derivatives with respect to both y and x. Looking at the time. This involves partials with respect to y and x. Unless mu is a function of just x, or just y, this is a PDE. And those three letters should strike terror into your heart at this point of your life. It means partial differential equation. This is, of course, an ordinary differential equation, which you've got to get really good at to even be allowed in polite society to utter the words partial differential equation, much less solve them. It's a really hairy, really difficult process that usually doesn't work. You usually can't solve the things. Okay, it's really going to stretch. You got to use everything you know and more. So we don't do this. That's not in the scope of this ODE course, where ODE means ordinary differential equations. Okay. But if we assume that mu is a function just of x, then mu y is 0, so we only have mu x m equals this. And that's an ordinary differential equation that we might well be able to solve. Might well not be able to solve it because there are plenty of them we can't solve. You don't know what's going to come out of the woodwork at you, but that's the situation. And if mu is just a function of y, then mu x m is going to be 0. And again, you get an ordinary differential equation just in y. Okay. Well, we're having so much fun that we want to go ahead and complete this. Now I wish I had 2 half boards, but I don't. So one of my goals for this weekend is to take 2 minutes and cut one of these boards in half. A little complication to that is you want another board on top of the sacrifice board to keep one side of the board from getting obliterated. But then the board I just wrote on has a back that I can't use. So if I cut that one with the black part down, so we'll cut upwards and screw up the back of the board, which doesn't matter, and leave the front. So that's going to be my strategy. If I had a fine-tooth blade in the saw, it'd be better. Okay, well, mechanics of the process aside, I'm going to get 3 half boards instead of just 1. Okay, well, what I've got here again is our integrating factor u must satisfy. Okay. Now I've got to peek to get it right. I can do it in my head, but it's going to. To make sure we have the minus there because my head isn't totally oriented. And that's going to be mu times either m minus n or mx minus n, my minus nx or nx minus my. It's mx minus ny, and I think I said it wrong. Okay, mx minus ny. A little hard to read that n, but it's an n. Okay, suppose mu equals mu x, just a mu of x, just a function of x. Then negative mu x n equals this because mu y n is 0. U y n and okay, mu y has to go with n and this has to go with m. I'm going to look again just to make sure I did that right. So easy to get it backwards, but for once I got it right. Okay, we have this. So mu x equals mu times mx minus ny over n. We could write that as d mu dx equals mu times mx minus my over n. And linear equation. Or at least it might be linear equation. Okay. If the equation turns out to be linear or separable, go ahead and solve it for mu. If it doesn't, you might try some other solution method. Maybe it's homogeneous. Maybe it's something else that you know how to solve, at least at some point in your life. But if it isn't linear or separable, your chances go way down. Now, you could do the same thing if mu was just a function of y, in which case mu x would be 0 and you would have this. And when I wrote this as n, I wrote this as n. This should be m. Doesn't make any difference in the fact that maybe you can solve this and maybe you can't. But there you have it. Okay, well, that's the method. You have examples in the book that show you how it works out, and the algebra and so forth of solving these things is no problem. If you have an equation and you're looking for an integration factor, then this is the process you're going to go through. Try to understand the process in general, follow it, don't just skip to the end, and see how it works out. Look at the examples. And then you have a couple of equations that are fairly simple where you are asked to try to find an integration factor. Okay, well, I haven't been able to address solution by substitution, but we'll do that fairly thoroughly on Tuesday, and we'll look at some problems you might or might not run into with exact equations.